All right, IBAASL2 kids. Today we're starting section 5.2 where we're going to actually start using the word derivative. Derivative is a big part of the calculus we're going to be doing this course, and today we're going to take some baby steps into it. Now, when I say baby steps, the first introduction to it is a little bit algebraic and slightly confusing, but then towards the end of this lesson, there's a pretty straightforward tool for finding derivatives that I'm going to show you guys. First up, the average rate of change. There's that word again, change. Remember, calculus is all about how things are changing. Is going to be delta y, delta being that triangle, it's a Greek letter, over delta x. So change in y over change in x. That's going to be f of x2 minus f of x1 all over x2 minus x1. That might seem kind of confusing, but if you think about 2 points on a line, the first one being x1, and instead of saying y1, you can say f of x1. Because instead, f of x is the same thing as y. So if you put an x1 into a function, you get an f of x1 out of a function. If the second point is x2 is the input, then out of the function, you would get f of x2. So this part looks very confusing, but it's actually just a sneaky way to say rise over run, or this is slope, essentially, which in the IB curriculum is the word gradient. We've gone over that, but I'll say it again. So it's like, y2 minus y1 over x2 minus x1. It's just a fancy version of it. Fancy slope. Slope is a big part of derivatives, which are a big part of calculus. In this diagram that I've drawn here with this kind of roller coaster cubic curve, we're going to talk about the word secant and the word tangent. Now, a secant intersects the curve at 2 points. So if I draw in a secant here, it might be something like this. Notice that it hits at 2 points. I realize that over here, if I were to continue this line, it would actually intersect again over here, making it 3 points, but we're not too worried about that. It's just a secant at, to the curve at these 2 points here. It doesn't matter if it hits other places as well. So this is your secant. Now a tangent touches the curve at exactly 1 point. So the way you can picture this is that it's like I always think of like a surfboard on a wave. It can only touch one part of the curve of the wave. So if you think about like this being your surfboard, I meant for that to just hit one spot. It just barely touches the curve. Like it comes by, we're going to redo that, it's kind of sloppy, and touches the point barely right there on the curve. This is called the tangent, or it's a tangent to the curve. It's a line that touches the curve in exactly one spot. Now, if you were to look at a parabola like this, a quadratic, and I were to draw a line that goes, from, let's say, these two through these 2 points. This is a secant line, and if I add the point x1, y1 for this first part here, and x2, y2, which I could say, f of x1 and f of x2 for those things, but I'm just going to use y's in this case. We could use our slope formula to figure out the slope of this secant line. But the question becomes, like, how do you find, get rid of these and draw something else on the diagram. How would you find the slope of a tangent line? So let's say you have a tangent that just touches at one spot on the curve. You can't find the slope of that tangent line with only just 1 point. Like to find slope, you need 2 coordinates to do your y2 minus y1 over x2 minus x1. So the strategy with a lot of this calculus stuff is to take a secant So let's say a secant goes through this point right here. Oh gosh, I'm not going to be able to line this up. Yeah, that's pretty close. So that touches at this point here and this point. And that's a secant line. So with these two coordinates, this one and this one, we could find a slope between those two lines. So then, if I take that secant line and I slide it a little bit closer, so let's say like I make it go through, oops, this point right here. So you can see this is another secant line that touches at 2 points, being this one and this one. So we could find the slope of that secant line. Now, notice because I slid this point a little bit closer to this position, that it's the slope of those secant lines are getting closer and closer to the slope of the tangent line. So like here, the slope of this secant line is very different from the slope of the tangent line. But when I change it and slide that point a little bit closer, this slope becomes more similar to this one here. The thought is if I keep sliding this point right here closer and closer to this point, that the secant slopes are going to be closer and closer to the slope of the tangent. So eventually you get to this point where, like, you know, if I pick a point that's really close to it, like right here, my diagram's getting a little convoluted, but something like this, that now that secant line, using these 2 points, you could find a slope of that secant line, and it's getting closer and closer to the slope of the tangent, which only goes through 1 point. If you were to take that point right here and slide it infinitely close to this point, maybe I need another color in here. If I slide this guy closer and closer and closer, you know, put it here and then here and then here and then here, eventually it's so close that we basically say it's like it's going through 1 point. It's just going through this point right here. And we can find the slope of that tangent using limits. So this is kind of the definition of a derivative. We'll get into it, but it's like slope. It's finding the rise over the run, but when the run here on the bottom gets smaller and smaller and smaller. So here I said that that's the definition of you know, the slope of the secant line as h approaches 0. So that's as h gets smaller and smaller and smaller. You can think of h like this distance. If I were to drop this down here, that this would be your h value. But then as I scoot that point closer and closer, like here, the h value gets smaller and smaller. If I put the point here, then the h value gets smaller. And if I put the point here, then it's smaller and smaller until you get these h values that are just little tiny chunks so close to the point that you can say it approaches 0, and you can just find the slope of the tangent. Now, what we're doing with all this is actually finding a derivative. So this is called the derivative of f with respect to x. So, little notation for you. Well, first of all, I'm using that word derivative, but really what you need to think of it as is as a slope machine. You'll hear me use this word a lot in class. A derivative is just a function that helps you find slopes of tangent lines. Derivatives are all about tangent lines. So, the first notation here you'll see is f prime of x, and that's the way you say this. F prime of x. It's a little like apostrophe on the f. The other one that you maybe doesn't come up as often but does come up is this guy right here, dy over dx. This is called derivative of y with respect to x. Okay. We're going to do a word problem that is definitely the harder example that we're going to do today. And then after that, I'll show you guys a cool derivative tool. And then the examples are pretty easy. So we've got this particle moving in a straight line. Its position is modeled by this, s equals 3t squared, where t is time in seconds and s is in meters. So part A is we're going to find the average speed from t equals a to t equals a plus h. So what that means is we're going to put a into the function. So like here's our t value right here. We're going to replace that t value with t equals a and with t equals a plus h, and then essentially find the slope between those two things. So the average speed here is just the slope. It's like the total distance traveled over the total time. So total distance is like your rise in this case, because you know the outputs are the s's in this function here, and those are the you know, your y values, so that's change in y, and then the x values are the time. Well, I mean the t values are the time, but they're the input of the function. So really they're asking us to find the slope between these two places, t equals a and t equals a plus h. So let's think about this in terms of coordinates. The first coordinate is going to be feeding a into the function. So if I put an a into the t spot right here, we're just going to get a 3a squared. So our first coordinate, sorry for all these zooms, is going to be a input, 3a squared output. That's the first coordinate. The second one is when you put a plus h into the function. So you're going to replace this spot once again with a plus h. So that means we're putting a plus h into it, and out of it you get a 3a plus h squared. So once again, input, output. Now we have two coordinates that we need to find the slope between. So we're just going to do like y2 minus y1 over x2 minus x1. Here we go. y2 minus y1 all over x2 minus x1. Now we need to do a lot of cleanup. The first thing I notice is that this a plus h squared, that we can FOIL that out. So the 3 will just hang out on the outside, and then the inside will be a squared plus 2ah plus h squared. If that's not immediately, like if you can't see that, you can always do a little sidebar to FOIL that out. So the sidebar would be, you know, I'll do it in blue right here, a plus h times a plus h, and then you get a squared plus ah plus ah plus h squared, and then there's two ah's in the middle. Now in the bottom, there's actually kind of a neat simplification because the a and the negative a cancel each other out, so we're left just with h in the bottom. Let's continue to simplify. I'm going to take this 3 and distribute it to all 3 of these chunks. So we get 3a squared plus 6ah plus 3h squared minus 3a squared, all over h. Now, can we simplify any more? Yes, we can. This negative 3a squared and 3a squared go away. So this is 6ah plus 3h squared. Ooh, and you know what? Oh, all over h. Oh my gosh. What just happened? Oh my gosh. Come back, please. No, wait, what class is this? You guys, that is unprecedented. That has never happened. Oh my gosh, it got rid of some of my work. Okay, we'll catch up real quick. Hopefully the recording's okay. Now, notice in the top that both of these terms have an h in them, so you can actually factor it out to get h times 6a plus 3h all over h, and then this h and this h cancel each other out. So we are left with 6a, did I miss something? No, I think it's all there. Yeah, 6a plus 3h, and technically in terms of the problem, this would be meters per second. So you can say meters per second. That is the instantaneous, or not instantaneous, it's the speed between the point A and time A and time A plus h. Now that we have that, we have this model right here. The question is, explain how you could find the speed of the particle at the instant t equals a. Well, at the instant t equals a, remember that we were starting with t equals a and t equals a plus h. So if you're sliding that a plus h closer and closer to a, you're making the h value smaller and smaller and smaller. So eventually you get to the point where h is so small you can basically just call it 0. So we're going to say when h equals 0, that's the instantaneous point at t equals a. So plugging that into this guy right here, we get 6a plus 3 times 0, which this part just goes away, and you get 6a meters per second. So if you knew the value of a, you could just plug it into this right here to figure out what the instantaneous speed is at any time. Now, just big picture. I know you guys are thinking like, oh my gosh, what is this problem all about? It's so hardcore with the physics and the algebra and blah, 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 and what am I even doing? Never fear. Essentially what we did is we took this right here and we found a derivative. Now we did it using kind of a definition and a limit approach to derivatives. I'm going to teach you guys a little bit of an easier way to find a derivative, so you don't have to do all this right here. But you will be expected to do maybe one problem like that down the road, but most of them will be using the tools we teach you. Speaking of those tools, differentiation. This is a vocab word for finding a derivative of a function. You can also call a derivative a gradient function or a slope function, or as I call it, the slope machine. So I'm going to throw some things onto this table, and I'm going to show you guys the derivatives of these functions. See if you can spot the pattern with these. The derivative of y equals x squared is 2x. The derivative of y equals x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. You guys seeing it? Do you see the pattern between this, how this turns into that? Can you make a prediction for y equals x to the 5th? You are correct. It's 5x to the 4th. Notice with all of these that if you're taking the derivative of x to the something, that the power comes out in front and then you drop the power down one. So the 5 pops out front to come right here. And then the 5 drops down 1 to become a 4. So if we were to do y equals x to the 25th, this would be 25x to the 24th. This is known as the power rule for differentiation. It only works on things that are in this form of x to the n. So anytime you're trying to take the derivative of something that's x to the n, you're like, oh, boom, just use the power rule. It's the old pop and drop, where you pop this guy out in front and then drop it down 1. So if you bring the n out in front and then drop it down 1, you get n times x to the n minus 1, which is the same as this right here. Very powerful derivative tool. Powerful, get it? I didn't mean to do that. Let's use that power rule. We're going to do 3 examples, and it's not going to take us very long. This first one, you would bring the 11 out in front and then drop it down 1. So f prime of x is equal to 11x to the 10th. And it's done. That's it. That's the derivative at 11x to the 10th. This next one is almost ready to take the derivative, but it's not in the form of x to the something. So we got to do a rewrite. Here, I'm going to put a little between these guys. So the rewrite is that f of x is you got to bring that power back upstairs and make it negative. Then you can do the old pop and drop, where you pop this guy out in front and then drop it down 1. So f prime of x is equal to negative 4. Now, here's where some students will make a tiny mistake. They'll say that it's x to the negative 3. But that's not you subtracting 1. You have to subtract 1 off of negative 4, which makes it more negative. So it's f prime of x is equal to negative 4x to the negative 5th. And they leave it like that. Negative exponent. Cool. This one is very similar, where you have to do a rewrite before you can take the derivative. And the rewrite is making it a rational exponent. That this is x to the 1/2. It's the same thing as a square root. Then you can do the pop and drop, where you put the 1/2 out in front. So to find f prime of x, it's 1/2 out in front times x to the, but then you have to subtract 1 off of 1/2, which is negative 1/2. All right, you guys, I realize this was a big lesson, but there's really only 6 homework problems, and they all use the power rule, so not too shabby today. I look forward to seeing you in class and working over homework questions.